and that way I can make sure I answer these questions. Otherwise, definitely as we're going through this, ask questions. Okay. And I say that for a couple of reasons. So we're into our second day of using logic. And can everyone hear me okay? Is that we okay? Okay. I'm trying not to annoy other customers here. But first off, we're in our second day of logic, okay? And sometimes the while logic that we're going to be looking at today can be a little bit confusing. And I want to give you two ways to do it and emphasize one of them. And then the second thing is that we're going to work through by hand how to calculate a square root, okay? And that's actually what we're going to use for our implementation. And so if this is something you haven't done before, this is one reason why I wanted to step through it, and have you have an opportunity to ask questions as we do it. Okay. So I guess maybe my first question would be, is who in here give me a thumbs up if you've taken a square root by hand, like without putting it in the square root into the calculator. Elliot, Brooks, Gabriel, good. Karen, Colton. Okay, fantastic. Okay, so this may be old news for you. So bear with us all. Let me make sure I can see what I need to see here. Well, then what we're going to do is we're going to take the square root by hand. This is actually the Newton method. And so it's based on a Newton rap sum, which we're actually going to do later for finding just a root. And so another way to call this is the divide and average method. Okay, so divide and average. And so what this is saying in the divide and average is, I'm going to write out, it's I of x plus 1 is equal to, or xi plus a divided by xi divided by 2. Okay, and this is if we're taking the square root of the value a. Okay, and so essentially what we're saying here is that this x sub I is going to be an approximation. Okay, and I want to emphasize that word. Okay. And you'll see how this fits into while loops in just a moment. But it's an approximation of a square root. And it's the type of thing where every time we iterate, okay, we'll do the first iteration. Okay, and that's what our subscript is in this subscript notation. Our first iteration, and that's going to be the input to give us the next iteration. So and in this iteration, we're putting in an approximation, getting out an approximation, and then we're going to loop through this over and over and over. Okay, is this the method that those of you that have taken a square root by hand, is this what you've done before? No? Give me a thumbs up if this is the method. Gabriel has. Okay, good. Okay, and so once again, this idea of an approximation is a really key concept, because this is really the first numerical method that we're doing in this class. Okay, everything else has been we're dealing with numbers, we're dealing with arrays, but it's nothing that you're going to not see in just a procedural programming class. But here we're actually going to approximate something that it fits into just fits into a bigger world. We've used square roots all the time, cube roots, and that kind of thing. And so let's just work through this, and let's use a root that we all know. Okay, and so let's work through this process using the square root of 16. So we want to find the square root of 16. And this seems kind of silly. I mean, we know that square root of 16 is equal to 4. But let's use this method. And to do this, I want you to make a table. So on the left-hand side, write out iteration, draw a vertical line, and then approximation. Leave some space here because this is where we'll do our calculations. Okay. and then keep on drawing your line all the way to the right, okay? And we'll use this space over here a little bit later. So when we are looking here for our first iteration, we essentially need to make a first approximation of what the square root is. So in our first iteration, let's have, so it's I is equal to 1, okay? So we've got an index that we're working through, okay? And our x of 1, we're gonna say, you know what? I'm having an off day, just a really bad off day. I see square root of 16 and I just throw down 8, okay? Because I've just forgotten exactly what that is. Well, then we need to calculate, okay, for I is equal to 2, x of 2, we're going to plug it into this formula, okay? It's the divide and average, okay? So we're dividing and then averaging with itself. So our approximation is now going to be 8 plus 16 divided by 8 divided by 2. And so thankfully that's a nice whole number. Okay, we get 5 because 16 divided by 8 is 2, 2 plus 8 is 10, and then divided by 2. Okay. And then, but, you know, we could stop there if we wanted, okay? But, you know, that just doesn't quite feel right, okay? And a lot of this is we're just going to say it's kind of based on feeling, right? I guessed 8, 5, ooh, that's kind of a big jump. So I don't think I'm getting quite close yet. And so let's do it one more time or another time, okay? And we'll get our approximation when I is equal to 3. And we'll do that by plugging in 5 plus 16 divided by 5, and then dividing the whole thing by 2, okay? So this is
Why
where
are you doing 16 divided by like 8 and 5 and not 9?
that's a, oh, and not 9.
Yeah.
It's because our A, we're finding the square root of 16, okay? And this is the formula for the square root of A.
Oh, I'm sorry. That's an A over xi, not 9. My bad.
I realize my handwriting isn't helping here.
Sorry about that.
No, that's fine. So the formula that we're using each time is going to be 16 divided by the previous approximation. Okay. All right. Is everybody good with this? Okay. Give me a thumbs up if you're with me. Okay. Cool. This on Brooks. Okay. I think we got most people with us. So just to make sure that we're on the same page here, this formula, okay, using the Newton-Raphson or the Newton method, we're looking for the square root of A, and the formula is x sub I plus A divided by x sub I, all divided by 2. Okay, so the divide and average. Okay, we're dividing the operand, okay, divided by our approximation, and then we're going to average it with itself and divide it by 2. Okay, just happens that this formula works out really well. And so now on our third iteration, our second iteration, our approximation got better. Okay, we started out at 8. Next time we got 5. Okay, we know our answer is 4, so we're getting closer. And so now we're going to plug in 5 to this formula. Okay, so x sub 3, or iteration 3, so x sub 3 is going to be the x2, which is 5, okay, plus 16 divided by 5 divided by 2. Okay, and that's going to give us our x I plus 1, which is 3. Okay, and so here, when doing this calculation, so 16 divided by 5 plus 5 divided by 2, and I get 4.1. Okay. And so then we move on to our next iteration. Okay, now 4.1. Okay, so the question would be is that if we didn't know this is 4, how would we know when to stop? So let's just keep on going because we know we need to go, but keep that in mind, right? If we were going to take the square root of, let's say, 23.6, we still need to know when to stop. And so here we're going to plug in our 4.1 plus 16 divided by 4.1, then divide that by 2. So I got 4.1 plus 16 divided by 4.1, then divide that by 2. Okay, now I'm getting 4.001. Okay, so we're getting closer and closer and closer. All right, so here's a question for you. Okay, and I posited it just a moment ago. How do we know when to stop? What would you do, okay, if we were given, some other problem that we didn't know the answer to? How would you know when to stop?
You would take a certain number of decimal places, and you would choose that number of decimal places. When that decimal point, like when that digit stops changing, that's when you've gotten your answer.
Okay, so Elliot is saying, I'm going to be looking at decimal places, okay, and when let's say I want it out to 3 decimal places, and if this digit stops changing, okay, then I want to stop. That is a great way to do it. That's called a convergence criterion. Okay, we'll talk about that later. Okay, in this problem, we actually have a better way to do it, a different way.
Is it like subtracting one number from the next you receive and then getting that number to the lowest possible?
Okay, and who was that said that?
Sam.
It was Sam. So yeah, Sam, that's similar to what Elliot was saying, where we've got 4.1, okay, and then we've got 4.001. And is that what you're saying, the difference between those two?
Yeah, I was thinking of just calculating the difference rather than analyzing the change in decimal places.
Yeah, and those are both similar concepts, where we're looking at something converging, okay, to a particular decimal place, or what you're saying is a particular interval, okay, and that's a type of tolerance to use. So that's going to be the word that we're going to use with this, is tolerance. Okay, I'm still going to say there's a better way to do this with this particular problem. Okay, and this isn't something we always have access to, but it is true here. To see if we've got the right answer. What is our value that we're taking the square root of? I mean, what is that number? We're taking the square root of 16, right? So a way that we can do this, and actually the two things that or the way that Elliot and Sam had suggested is a convergence criteria. In this case, we can actually use an error criterion. And so let me think about that, or let's think about that for a second. Is that, let's go back to our first approximation. Our approximation is 8. And so with this approximation of 8, then we could compare that to 16 by taking the square. I mean, it's by squaring 8. Okay? So I want you to make another column where we have xi squared. Okay, and so when I is equal to 1, if we square this is equal to 64. Okay, and so then that means that we can compare 64 to 16. And then we can come up with an error, okay, and that error would be xi squared minus 8, okay, which in our case is 16, right? So we get, for this error, is 64 minus 16 is equal to 48. And I put this as an absolute error, okay? And so typically in these types of problems, okay, we're trying to minimize an error. So make it, once we get down here, we want our error to be 0 or really close to 0. We can see here that our error is 48. All right, give me a thumbs up if you're following me here. Colton, time.
I have one question. That number converges though on the answer, right?
That number would converge on the answer, right? So we do know it should converge, okay? And I'm gonna separate these criterion a little bit of a convergence, okay, versus an error convergence versus a difference convergence, okay? It's all convergence, and I see what you're getting at. That is the right term no matter what. And so here we are looking at 48, okay, as being our error. We want that to converge to 0. So you're exactly right about that. So then, so for our error, for our next one, we're going to get 5, and if we square it, we get 25. And we're going to use the 25 minus 16 as our error. So we can see that our error is getting smaller. And then for our next one, if I square 4.1, I get 16.81. Okay, so we're getting close. 16.81 minus 16 is equal to 0.81. And then if I square 4.001, then we get 16.008. Okay, and 16.008 minus 16 is equal to 0.008. All right, so again, we're left with the question, is this good enough? Is 4 times 3 this good enough? Would you be satisfied in this case? And how do we decide? So let's do it one more time. Okay, let's go 5 times. And so our fifth approximation, let's put in 4.001 plus 16 divided by 4.001 and divide by 2, and we get 4. Let's see here. So plus 16 divided by 4.001 divided by 2, I get 4.000109881. And so if I square that, I'm now getting 16 point, we'll just say 001, and then 16.001 minus 16. I now have an error of 0.001. All right, so as we work through this, we've come down to an error criteria now, where our error, okay, we're saying needs to be, or we've hit a point where it's less than or equal to 0.001. Okay, so I'm going to stop right here, and with this example, who's not following me so far in this example? Give me the party symbol. Fantastic. Okay, this is good. Okay, so the reason why we're doing this, okay, and now we're down to that question of within 3 decimal places. Okay, and I'll put it just how Elliot did earlier. And our error is within 3 decimal places. Okay, so we've now defined, if we're satisfied with this, a tolerance, okay, for those for that particular decimal place and for that condition. All right, so so the key points, and this is where we're now going to take a look at how to put this in MATLAB, because we need to do a looping. Okay, as we're going through this, it's an iterative context or iterations of what we need in order to get the answer. Okay, and we have to work through our loop. Okay, doing iteration 1, 2, 3, 4, 5, and then we've got to stop it sometime. And so our stopping criterion now becomes some sort of tolerance. Okay, and the tolerance can be based on many things. Here, it would be an error tolerance. Okay, we're going to say that we want our error to be less than or equal to 0.001. And if you're familiar with while loops, then I hope that you can kind of see the structure here where we're defining our problem. And then in the while loop, our error tolerance lands in that conditional expression. Okay, and it's the series of commands below it, okay, that are our divide and average method. Okay. So there's some starter code. There's some starter code. I want you to pull that up and get ready for it. And really the kind of two big things that we've got to do is that you had an opinion, okay, or at least I hope each of you had an opinion as we were working through this as to what level of error you were willing to accept, what level of tolerance, okay? And I want you to just think about, you know, this idea of tolerance, okay? And we're not going to dive into this in any deep way today, but it is going to show up the rest of the quarter in a lot of the problems that we do. Okay, this won't be the last time that we do a while loop, and but it's essentially saying you've got a standard, okay, and your standard might have been pretty happy with 4.1, okay, or it might have been pretty happy with 4.001, okay, or now 4.0001. Okay. So it looks like I got my decimal places wrong here. Whoops. Zero, zero. No, that's right. Okay. And so, and then continuing that, you know, we didn't know when we would stop. Okay. So let's get into this looping here and program this into MATLAB. So if you pull open the starter code for the square root, divide, and average, then what we need to do here this guy off. Just 1 second, guys. I'm going to stop sharing my screen just for a moment. Got to find the file. Oh, I think my computer is stopping. It's not responding. Okay, sorry for the technical difficulties. I see something in the chat. Elliot says that I equals 6, my calculator rounds off all the error. Why would that be? Elliot,
It's just my calculator only stores a finite number of decimals, and so after a certain point, it just throws away the extra, and it's like, well, it's 4.00000, so it's just 4.
Yep. So
Though, isn't MATLAB also only storing a finite number of decimals? So you could just say, well, x squared not equal to a, and then eventually it would get there.
yes. So Elliot's asking a good question. I addressed this in one of the office hours one time. So let's diverge just briefly into this. There's only one more iteration that Elliot could have gotten to on his calculator. I'm using like a TI 30X solar calculator. And so it's going to run out of capacity to store decimals as well. And the reason why that occurs is because in how our calculators work, how MATLAB works, how our computers work, is that we have a certain number of decimals, and it's based on the bits that are available for computation. Okay, so 8-bit, 16-bit, and so forth. And so I want to show you a command really quick. If you type in EPS, which is called the epsilon, you're now going to see, okay, how many decimals, at least to 0, that MATLAB can handle. Okay, based on the fact that like I'm working on a 64-bit system, and how MATLAB and everything kind of fits into this. The EPS, which is the epsilon, the computing epsilon of the computer, tells us how far we can go out. So most likely, your computer, okay, is going to be a 64-bit computer. You're probably going to get the same answer. You're going to be able to store a lot more decimal places and a lot more resolution than what you can with your calculator. Okay, does that answer your question, Elliot? As to why you
Yeah,
couldn't go
but like the computer's doing the while loop. Since I don't have to type it in every time, why don't I just have it do it n times until it, does it?
That's a good question. So that's up to the tolerance that you want. So is it 2 times? Is it 4 times? And it also depends on how good your guess is. So your approximation. Okay, so there's a lot of factors that'll fit into that, and you can see this, and you'll be able to, after today, you'll have some code that you can mess around with the types of tolerances on this type of approximation. Okay, sorry for the technical difficulties. So let's program this. Okay, let's actually get into a while loop and figure this out. So so pull open your code. I've already put some pseudocode in here. Okay, so that we can just do this together. And so in looking at this, we need to define the problem, and we need to have an acceptable tolerance. Okay, and our tolerance is going to be on the error. Okay, and then we'll get into our while loop. And actually, let's take a glance at that while loop. Okay, it's a while loop. You have to have an end statement and then that conditional expression. So when we come down here into our approximations, okay, down here is where our while loop is going to go. So you can just go ahead and put that in there, a while and an end. Okay, and then up here, defining our problem and acceptable tolerance. Our problem, we had a is equal to 16. Okay, that was, I think I said operand earlier. I think it's actually radicand is the name of it, of what actually goes underneath the radical. And so then let's create a variable called error tolerance. And so let's put in 0.001. That's what we want to get under. Okay. And then because we're going to be comparing our actual error to our error tolerance, okay, when using a while loop, okay, this loop is going to compute and compute and compute until the conditional expression that we have is not true. Okay, so while it is true, it's going to continue going. So the way that we would state that is that while our error is greater than our error tolerance, then that's the number of times, okay, and that we want to allow it to go. And once this statement here is false, it's going to stop computing. Okay, are you with me on this concept of a while idea? Yeah. And so we want to, so we've defined our problem, our acceptable tolerance, and then we want to give our first approximation, which is a guess. Okay, and we said that, all right, when I guessed for that first time, I guessed x equals 8. It's a really bad guess. Okay, but that's what we were going with. And then we also need to have, coming into this while loop, we have to have an error itself to be able to make that comparison, right? I mean, because if we ran this now, all right, we're going to get an error, and it's say unrecognized function or variable error. So let's come up with our error. Our error is going to be, we said it's the absolute value of, and it's x squared minus a. Right, so we're always comparing it back to 16 in this case. And so now, okay, I just ran it. We know that our error is greater than our error tolerance. But now when I've ran it, what's happening? Anybody, what in the world's happening? What's that?
Because there's nothing in the while loop.
Yeah, so what is it doing? We are now in an infinite loop, okay? It's continuing to go. You can see down here in the command window, there's just nothing, okay? It's not getting anything out. And that's because this statement here, error is greater than error tolerance, is always going to be true. So we got to put something in here that's going to make that not true to make it stop, okay? So Control C is whenever you're in an infinite loop, whenever you've got something that you're just exploding in matrices, you run out of memory, or just things are taking forever and you're getting impatient. Okay, press Control C, and that is your ability to terminate the script in the command window. Okay, is everybody good with that? That's going to save your tail a lot. All right, so then as we're looking here for our error and error tolerance, and let's see here, we even see here our error was 48, like what we calculated earlier. Okay, and then what we're putting inside the while loop is we now need to recalculate the error. Okay, but we only want to do that after we've then put in our divide and average method. Okay, and that was x plus a divided by x all divided by 2. Okay. And so as we jump into this loop, okay, this statement is true as it begins. Okay, we're now taking the x, which is 8, into the loop, and it's 8 plus 16 divided by 8 divided by 2. Okay, and that's going to give us the new value. Okay. And then we then need to calculate our error again. Okay, so we're going to use the same error metric. Yeah. Okay. And then now that this error term is being updated as it works through the while loop, okay, there is a possibility now that this error will not be greater than the error tolerance. Okay. And then that's going to give us our stopping point. And so let's go and run this. I'm going to take off the suppress outputs with this. Let's clear a command window. And we should see what we had on our piece of paper is that in the first time that it calculated, x is equal to 5, our error was 9. The next time x was equal to 4.1, error was 0.81, then 4.001, and so forth, until we get down to x is equal to 4.0000, and our error is 1.4868 times 10 to the negative 6. Okay, so that was the first iteration. Okay, it went through multiple times until it was below our error criteria. Okay, and then the next part, of course, we want to display it to the user, as we do in all of our situations. So do your format, short G, and then let's do something like display, and then we'll create our string in here that says square root of remember the num to string command. So the square root of, that'll put 16 in there, is, and then num to string of x. So that'll be our final x at the end. I'm going to suppress these outputs again. And hopefully, yeah, so now we get to the square root of 16 is 4. All right. So this whole idea of looping, and looping when we don't know the number of iterations, okay? We could give it the iterations, and that would be a different type of loop. That would be a for loop. We're going to talk about this on Monday. But when you've got something that you don't know when to stop, okay, this is one of these situations. That's where we're going to define a tolerance, okay? And then once we meet the tolerance, then we kick out of this loop. One thing that I want to point out here is that there are two different ways to do a while loop. And so one of them is the while loop. That's the classic while loop that we just now did. However, I'm going to recommend that you do something called a while break loop. Okay, so take a look at this syntax and let's work through this. We have the while command, and then we have the end. Okay, just like we've had before. But notice here is that in coming into the loop, we've got a 1 there. So while 1. And so that should tell you that it's going to allow you to enter the loop no matter what, because by putting in a 1, it's saying it's true. Okay, and so here you've got an opportunity, or to get out of the loop. Okay, is now you're going to put in a conditional statement. Okay, and it's just like we did yesterday in our decisional programming. If the conditional statement is true, then it runs this command, which is break, which is going to kick you out of the loop. Okay. Now, the advantage of the while break loop versus the while loop is that this conditional statement can go anywhere you want within the while loop itself. Okay. So in other words, your conditional statement can be up at the top. It can be the very first thing that you check on, right? So you jump into the loop and you can test your condition. Okay. Or you can execute a series of commands and then test your condition. Okay. Or execute all and then do more commands. Or you can do all of your commands and test your condition at the end. Okay. So it's like a pre-test, what would be called a pre-test or a post-test or a middle test. Okay, for this. And this gives you the flexibility to actually streamline your code a little bit, make it a little bit more understandable. Okay. And so over here, let's go back to our code here. Hopefully you see at least one point of inefficiency, which is that we had to run this line error twice. Okay. And so, but by using a while break command, okay, we could put this error calculation within the while loop. Okay. And then test, have our error versus error tolerance. Okay. Have that be tested in the middle of the function, or the middle of the while loop rather. Okay. And then that's going to streamline and just make a cleaner coding experience. And so that's actually your homework. You'll be working a problem out of the chopper book that specifies for you to use a while break structure. Is this a distinction? Did you guys encounter this distinction in your procedural programming class? Like a while versus a while break? Give me a party if it was a no, or a thumbs up if yes, if you've seen it before. Okay. All right, so Carter's seen it. I always think that Sam is giving them a thumbs up because that's just his picture. So, okay. All right, so I think that, at least in my experience, this while break loop is going to be where you want to be, okay? Because you get the flexibility, you get to use these conditional statements and decisional pieces, and you just get much more control over it, okay? So, all right, so what questions you got on this? Give me a thumbs up if you're all good on all this information. Okay. All right. Give me a party if you're just lost. Okay. I don't see anybody that's absolutely lost. So that's good sign. All right. So there's one homework problem or one practice problem associated with this. I actually want to take the code that you've got here. Okay. And it's all specified in the chopper book where you're going to turn this into a function. You are going to use the while break structure, okay, for your while loop. Okay. Oh, also another thing about the while break, I meant to mention this. In the while loop, the loop will continue until the conditional statement is not true. And in the while break loop, that flips it on its head. The loop will compute and continue until the conditional statement that you're making here is true. Okay. So keep in mind those distinctions. Okay, which means you're going to have to change how you express your decision there, your conditional statement. Okay, so you're going to be creating this program using the while break and putting it into a function. And then also something about this method with the divide and average is that it's only good for positive values. Okay, so I want you to make it so that you're putting logic in there and outputting the right information from your function and handling the square root of negative numbers. Okay, so you have to deal with the imaginary numbers and output the imaginary numbers of this. All right. Okay, what are the questions you got here?